In another video, we talked about how you can take the molar mass of a substance that you have and using that information gathered from the periodic table, you can calculate the number of moles that you have given a certain amount of grams, or you can calculate the number of grams you have given a certain number of moles. And so we learned how we can go back and forth from mass to moles and moles to mass using that information. Now, if we are calculating the number of moles that we have of a compound, or the number of grams that we have of a compound, then that changes things a little bit because obviously we can't have that information directly on the periodic table because there's more than one atom involved. For instance, if we were talking about the molar mass of calcium chloride, what we have to do is think about the fact that if we have 1 mole of that compound, then it's also true that we have 1 mole of chlorine atoms and 1 mole of sodium atoms. And now we can go to the periodic table and recognize that chlorine has a molar mass, if we are rounding to the tenths place, chlorine has a molar mass of 35.5 grams per mole, and sodium, according to the periodic table, has a molar mass of 23.0 grams per mole. And so the mass of the whole thing is going to be equal to those parts added together, the mass of those parts added together. And so we have a molar mass for sodium chloride of 58.5 grams per mole. And each substance that we are working with would be done essentially the same way. So for instance, if we had the molar mass of carbon dioxide, if we had 1 mole of carbon dioxide, then we would have, wait a minute, we got a little bit of difference here. Notice we have 2 oxygen atoms. Oxygen atoms have a mass of 16 grams per mole, but there are 2 of them in this particular compound. So we have to multiply the mass by 2, and we have a molar mass for the oxygen of 32 grams for every 1 mole of carbon dioxide. The carbon weighs 12 grams per mole, but we only have 1 of those in this compound, and so we do not need to double it. And we will notice that the carbon in this weighs 12 grams per mole. The whole thing is going to weigh 44 grams for every 1 mole. That's the molar mass, the mass per mole of carbon dioxide. And we could do other examples, but I think you probably get the idea. You can go back and replay it if you need to take another look. But we need to talk about what happens when you have a polyatomic ion and it is in parentheses where you have more than one of them. For instance, let's say instead of sodium chloride, we had calcium hydroxide. If we had calcium hydroxide combines in a 1:2 ratio of calciums to hydroxides. What this means when you look at what the 2 outside of the parentheses is indicating, what that's telling us is that we have 2 hydroxide polyatomic ions, which means that there are 2 hydrogen atoms. Hydrogen, according to the periodic table, has a molar mass of 1 gram per mole, but since there are 2 of them, we multiply that by 2. Oxygen has a molar mass of 16 grams per mole, but once again, since we have 2 oxygens, just like we had 2 hydrogens, we have to multiply by 2, which gives us a molar mass of 32 grams per mole for each of those oxygen atoms. Now when we get to the calcium, we only have 1 of the calciums in this particular compound, so we don't have to multiply that. And so we just add them up, and we notice that we have 74 grams per mole for calcium hydroxide. Let's do one more similar to that. Let's give ourselves something really interesting. let's say that we have aluminum sulfate. Aluminum sulfate. Aluminum sulfate combines in a ratio of 2 aluminum atoms for every 3 sulfate polyatomic ions. And so once again, the 3 outside of the parentheses is telling us that we have 3 of the sulfate polyatomic ions. And those have a 2 minus charge, which really we're more interested in the number of atoms that we have than the charge right now. But nonetheless, they are 2 minus polyatomic ion. Notice that you have 3 of these polyatomic ions, which means you have a total of 3 times 4, or 12 oxygen atoms. So those 12 oxygen atoms are going to have to be accounted for in the mass. So let's take this and at least for the moment, move it over here where it's a little bit further out of the way, but we can still have it close by to reference. And notice that what we have is, with our oxygen, we have a molar mass of 16 grams per mole times the 12 atoms that we have in each molecule, or excuse me, each formula unit of this particular compound. So we've got 16 times 12, and I don't trust myself doing this on the fly when I'm trying to concentrate on teaching, and so let's put it in a calculator. 192 grams per mole for the oxygen. Now when we look at the sulfur, sulfur has a molar mass of 32.1 grams per mole times how many? Well, if we have 3 of this particular polyatomic ion, then we've got 3 sulfurs, because each one of the polyatomic ions has 3, or has one of them, and there are 3. So we have 32 times 3, which is going to be 96.3 for the grams per mole for the sulfur. And now we come to the aluminum. When we're looking at the aluminum, aluminum is an individual atom. We have 2 of them, and each atom of aluminum weighs 27.0 grams. There are 2 of them. It's not inside the parentheses, so the 3 does not apply to the aluminum. And so 27 times 2 is 54. The mass of the whole thing is going to be equal to the sum of the different parts that go into it. And what we have is 0.3, 10, 12, that's 10, 19 and 5, 24, 342.3 grams per mole, if my math in my head was correct there, and I certainly hope that it was.